Predict all the alkenes that would be formed by dehydrohalogenation of the following halides with sodium ethoxide in ethanol. Oh my God. And identify the major alkene. Now we are talking about an elimination reaction called dehydrohalogenation. Now this is a very important reaction, and before we go around solving these problems, let me just give you a quick brief about it. What is the meaning of dehydrohalogenation reaction? D means removal. Hydro stands for hydrogen. Halogen obviously stands for halogen. Dehydrohalogenation means removal of hydrogen and halogen. Means removal of HX. Please note in this case, H is attached to one carbon and X is attached to the adjacent carbon. So, removing H and X together, the H plus and X minus together from an alkyl halide, to produce the alkene, this is called dehydrohalogenation. Please note, this is called an elimination reaction. For this, you need a strong base like sodium ethoxide in ethanol or alcoholic KVH. Yes. Anything else? There is a rule also when we talk about the major product, and that is called Zaitsev's rule or Zaitsev's rule. The real name is Zaitsev, the Russian scientist, but British started calling him by funny names like Zaitsev, and that has become popular. So it's the same person, Zaitsev. We'll just take up one example and exemplify what the rule also says. First, let us look at the first question. Methyl cyclohexane. Now, first let's take a cyclohexane molecule. 1 bromo, 1 methyl cyclohexane. Lovely. And when we talk about dehydrohalogenation, there is a method involved. And what is that method? See, listen to me with great concentration, simple method, you'll find it very useful. And then we will come to Zaitsev's rule also. Br is going to leave, right? And the carbon atom to which Br is attached is sometimes called alpha carbon. What? Let me repeat. The carbon atom to which halogen is attached is called the alpha carbon, right? And the neighboring of alpha is supposedly beta carbon. So what are the neighbors? Alpha, this is beta, and this is also beta. Oh my God. And the concept is that the beta hydrogen is removed by the base in dehydrohalogenation reaction. What? The beta hydrogen is removed by the base in dehydrohalogenation reaction. Okay. So, which hydrogen? Are the hydrogens here? Of course. If you see, this is HH, this is HH, and there are 3 hydrogens. So, if you call it beta 1, beta 2, beta 3, there are 3 possible locations. And by the very design, because of symmetry, beta 1 is same as beta 2. So when you cause the elimination reaction, I'll just write down the mechanism also for you. It is a classic E2 mechanism as they call it. I have Br, I have CH3, HH, HH, and let's take it like this. See, we have OET minus. It attacks a beta hydrogen. That means it donates a lone pair. This hydrogen leaves its electron, comes here, and it pushes out the halogen like this. Oh my God. This is the way? Yes. So this is beta hydrogen, this is the leaving group, and this is alpha carbon. Alpha carbon, alpha hydrogens, and this is beta hydrogen. What do you get? You get an elimination product like this. Okay. Where did the hydrogens disappear? They are very much there. They have not disappeared anywhere. Just that. Explicit hydrogens don't have to be written in bond line notation. You may write it, you may skip them. This is what we get. Okay. And what happens to this? You get ET, OH. Fine. and Br minus, of course. Done? Done. Sorry. Is there a minor product also? Yes. And what is that? I'll show you that also. You have Br, yes, and you have CH2H. Okay. So I use ETO minus. Donate, jump, push out. You will get this is also a reaction possible in case you have something which we were calling beta 3. 1, 2, 3 is arbitrary name given by me. There is no standard nomenclature there. Just to indicate that there are different betas. Now, I have this and I have this. Which one is going to be the product? Which is the correct answer? Honestly, each of these is possible. But then in organic chemistry, there is a concept of major and minor. Always you get something which is more favored and something which is less favored. This is major product and this is minor. In this case, major and minor was dependent on beta hydrogens. If you have 3 different types of beta hydrogens, you get 3 different types of products. So it's as simple as that. In our case, we had beta 1 was same as beta 2, beta 3 was different. So I have 2 types of products. Okay, that's fine. Anything else? Well, I guess that's it. Major and minor. Why is it major? Why is it minor? There is a rule, as I said, called Zaitsev's rule. Yeah, more honestly, Zaitsev's rule. Both are same. Even the person is same. Now, what is the rule? It says that the more branched alkene is the more favored alkene. If you are getting 2 different alkenes, then the alkene with more branches is the major product. How do I decide the number of branches? That's not very difficult. Just look at this. This is the alkene. Yes. What about branches? See, these are vinylic carbons. Now, 1 carbon, 2 carbon, and 3 carbon. This vinylic carbon is linked to 1 and 1, 2 carbons, and this is linked to 1 carbon. The 3 carbons. These carbons I'm talking about. So we say it is branched in such a way that it has 3 neighboring carbons. What about this? This alkene is branched in such a way that it has 2 neighboring carbons. It has 1 and 1, 2 branches. This has 1, 2 and 3 branches. More branched alkene is more stable. That is Zaitsev's rule, and more branched alkene is more favored product. So this is why this is the major product and this is the minor product. Second question mentions, now you have to solve this. You have 2-chloro-2-methyl butane. Now I have butane, I have methyl and I have chloro. Fine. Like this. Can I mark alpha and beta carbons? Yes, I can. Cl is here, so this is alpha carbon. The carbon attached to halogen is alpha carbon. The neighbors are beta carbons. And I have not 1, not 2, I have 3 beta carbons. What should I do? As elimination happens, I'll start getting different alkenes. With beta 1, if I remove hydrogen, I get a pi bond here. This. With beta 2, I get a pi bond down there. Actually, if you see, these are same. These are identical, there is no difference. So beta 1 is same as beta 2. What about beta 3? Let's try that. If beta 3 is eliminated, well, what you get is this. Oh my God. Now, just look at the level of branching. In this case, you have 1 and 1, 2 branches. There is no branching here. In this case, you have 1, 2 and 3 branches. This is good. This is great. Yes. So this naturally becomes the major product, and this is the answer. What are these? These are minor products. Fine. They're not even asked, but I've just mentioned them for your information. Now the third part. It says, well, we have pentane, 3-bromo, 2,2,3, trimethyl. Okay. This is the structure. Very interesting. Now, let's identify alpha and beta. This is alpha carbon, right? So this is beta 1, this is beta 2, and this is actually, you could say beta 3, but there is a problem. Carbon, 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 carbon. There is no beta hydrogen here. And if there is no beta hydrogen, obviously you can't eliminate from here. There has to be at least a hydrogen, right? So this is a quaternary carbon with no hydrogen. Already carbon has formed 1, 2, 3, 4 bonds with 4 different carbon atoms. There is no hydrogen atom here, so you cannot form a pi bond on this side. You can't make a 5th bond here. So only beta 1 and beta 2, I get 2 products. With beta 1, I can just write down elimination. How would that look like? First, let me write down the molecule. Well, this is pentane. With beta 1 elimination, I get this. With beta 2, I get this. And now the question is, which is more branched, which is more stable? This alkene has 1, 2 and 3 branches. This alkene has only 1 and 2 branches. There is no branch here. So this becomes the major product. And this is the answer. Yes, this is the answer. And this is now what conversions. How would you bring about the following conversions? Ethanol to but 1 ine. The first, let us write down the molecules and then we'll think about the methods. We have CH3, CH2, OH. This is ethanol. And we have intentions to change it to butane, which is CH3, CH2, C triple bond CH, but 1 ine. Try to look and imagine the steps you could actually conduct. Now, whenever you're faced with such questions, the first thing you must compare is the length of carbon chain. This has 2 carbons and that has 4 carbons. So first try to locate which carbon-carbon bond is the new bond. This looks like the new bond. This is the one which has been established. And what we're trying to tell you is a very popular method called retrograde synthesis. What is retrograde? Just work backwards, try to see what was there earlier. Now, I would get this if I have what? Which 2 species can react to give me this? How can I get this as a new bond? Well, obviously OH is not a very easy bond to break. Oxygen-carbon bond, if you have to remove and insert something else. What could I imagine? One imagination is this. What if I have CH3? Now, this is where you have to imagine. It is not written here and it could have more than one answers also. But say, had you had Br here or Cl, something of that kind, a halogen here, a leaving group. Okay. And what about this? C triple bond CH. And if I have minus charge here, wow, we have a nucleophile, yes. In case you mix these 2, what happens? Attack, kadak, classic SN2, and I will get this as the product. Yes, I will get this as a product. Fine. So that means that I get my 1-butane if I get these 2. Now I don't have them. All I have is ethanol. I have to prepare these. Can I prepare 1 and 2? Now let me think more. This is very simple possibility. If ethanol is divided in 2 parts, with 1 part, we just use PBr3. Ethanol with PBr3, it is halogenated to CH3, CH2Br. and the rest is H3PO3, which we don't need. So by PBr3 or PCl3 or PCl5, I will get simple alkyl halide. I can use it. So I have one already. Now I need two. How do I get two? This is not very difficult to see. That C triple bond CH minus, this looks a little ugly. Could I just get two from, if I have H C triple bond CH, I can remove one H plus, say using NaNH2, and I'll get C triple bond CH minus. Of course, there will be a cation which is pretty much useless, but yes, I would get this. But how do I get this alkyne? Now this also becomes a problem. Let me try elimination reactions, more drastic one. How exactly? Well, if I have CH3, CH2Br, great. Else, I could also use concentrated H2SO4, 180 degrees Celsius heat, and I'll get CH2, double bond CH2, I get alkene. I have to prepare alkyne, so at least let me get to alkene. And then, if I add chlorine, I get CH2, CH2, Cl, Cl, yes. And then if I use alcoholic KOH, I get vinyl chloride. And last and the least, if I use NaNH2, because alcoholic KOH is not sufficient for elimination for vinyl chloride. So now vinyl chloride, further one H and one Cl can eliminate, and I will get alkyne. And same NaNH2, if I add in a little more quantity, it can also remove one hydrogen for me, and I will get this. Is that fine? That's absolutely fine. This is the sequence, and this is how I will get it. The second conversion is nothing but a subset of the first one. Ethane to bromoethene. Wow. Now I have CH3, CH3. And I have to convert it to CH2 double bond CH Br. Bromoethene. Ethene, please note. How do we do this? Well, first of all, this bromoethene. Now, there could be many ways, but I suspect we would need to use alkynes. And if we have to use alkynes, let us start at least. Alkanes are not very reactive, right? They're called paraffins. So what do? First, Cl2H nu. Let me cause a monohalogenation. I get CH3, CH2, Cl. And then I use alcoholic KOH with heat. So I get CH2, double bond CH2. Beautiful. Why do we use chlorine and not bromine? Bromine is cheap, that's why. And then I add Cl2 in inert solvent like CCl4. I get CH2, CH2, Cl, Cl. Beautiful. No, let me be a bit more rich. Let me add bromine, not chlorine. Why? I need bromo, not chloro, right? So let's not be miserly. So I get Br, Br. I seem to be pretty close, yes. What do I need to do? All I need to do is add alcoholic KOH. If I add alcoholic KOH, one Br and one H. If I eliminate, the remaining CH2, CHBr or vinyl bromide would be the answer. I don't even need an alkyne. I could just manage with alkene. This is the answer. Propene to nitropropane. Now, this is propene. And this is 1-nitropropane. How do you do this? Well, honestly, nitro group is not a very comfortable group to insert. How shall we insert that? Well, this can best be done by nucleophilic substitution. If you use NO2 minus, normally oxygen attacks. You use AgNO2 if you want nitroalkanes. Okay. So what do? I take Br and add silver nitrite AgNO2. So AgBr will precipitate and NO2 group through nitrogen, because please remember NO2 minus is ambident nucleophile. If you want to connect through oxygen, use KNO2. If you want to connect through nitrogen, use AgNO2. Fine, I'll do that. How do I get this Br from here? This looks like one step. Now, I need to add HBr. But this looks like anti-Markovnikov addition. Yes. So use HBr and peroxide. Crash effect. So you get one bromo and that would give you one nitro. Just two steps. Now we have toluene to benzyl alcohol. This also does not look like much. We have toluene, and what we need to do is we have to oxidize this to benzyl alcohol. What is benzyl alcohol? Okay, so this H has to be changed to OH. Yes, my dear. How do we do that? Well, benzylic position is awfully easy to substitute. What do? You use bromine with NBS. NBS is N-bromosuccinimide. And when you carry out this reaction, selectively bromine gets substituted at allylic or benzylic positions. So what do I get? I get this CH2Br. Fantastic. Br has to be substituted by OH. What do? Add simply aqueous KOH or NaOH. You find that there will be a simple substitution. SN1 or SN2 both can proceed because carbocation is stable, nucleophile is strong. So both will be the combined mechanisms. You will get Br minus substituted by OH minus. Two steps. That's it. And then it says propene to propyne. Now these are easy ones. This is propene and somebody says, I want propyne here. Well, you're welcome. How shall we proceed? Let's take a look. I believe we have to remove hydrogens. Then we should first fuel its aspirations. Add chlorine. Fine. Let's add it. And then use alcoholic KOH. So what do you get? You get dehydrohalogenation. H and Cl can be removed and you get this. All you need is to remove one more HCl. How do we do that? Add sodamide. Vinylic halides can be removed using sodamide, NaNH2. Very powerful base. The end. That's it. Ethanol to ethyl fluoride. Now, how would you do that? Well, when you have CH3, CH2OH. Alcohols. Now, CO bond is difficult to break. The first thing you're supposed to do is treat it with something like PCl3. You get CH3, CH2, Cl. But we wanted fluoride. Yes, you'll get that. Now, treat this with silver fluoride, AgF. Please note, if you're treating this with PF3, you get nothing. PF3 is pretty inert, it won't react. But now you treat this. AgF is water soluble, while AgCl is not. So AgF will release fluoride ions, and now you can have a substitution CH3, CH2F, and AgCl will simply precipitate out. That would be a beautiful method for substitution. Bromoethane goes to propanol. Now bromoethane, this is bromomethane, CH3Br. And we are supposed to make propanol, which is CH3, COCH3. Now this sounds quite interesting. How should we do it? Where does this carbon go? What are the places it is going to connect to? Let's take a look and let's watch. There could be many methods, many ideas, or many, you could say, approaches for solving this. The simplest thing to add carbons, the first idea you get is use Grignard's reagent. Can we use Grignard's reagent? Well, we always can. How? Let's take a look. CH3Br can be with magnesium and dry ether. You could convert it to CH3 MgBr, right? And now there could be very different methods, like you could treat this with maybe acetaldehyde, CH3COH. If I might be allowed to use acetaldehyde directly, you would find that they would react and I get CH3CHO minus and I get a new CH3. This is my old CH3 and this is the red one. Red one comes from aldehyde. I get this. Now what do? Well, add H plus, you get CH3, CH, OH, CH3. And now I add an oxidizing agent. Any oxidizing agent like KMnO4 or K2Cr2O7 is good. And that oxidizes the secondary alcohol to ketone. Is that possible? Easily possible. Now, this is a very simple trail. A bigger challenge happens when you claim that all the carbons in acetone must come from CH3Br. If you have any such constraint, then the problem would obviously become much more interesting. I positively believe that NCERT is not going to offer you such problems, but still, we have solved the problem once. And again, let me take it to one more, even more deep solution and discuss that possibility also. What would happen if we just want all the carbons to come only from CH3Br? Can we do that? Yes, we can. How? Again, let me demonstrate that for you. You have CH3Br and I also have CH3 groups here. Now, could I use them directly? Yups. Use zinc. So you get CH3 whole twice Zn, dimethyl zinc. Now this comes as a very interesting reagent. Yes, indeed it is. And now on this add COCl2. What happens in nucleophilic substitution? Now this dimethyl zinc is similar to the Grignard reagent, but it is less reactive. So what happens is, it is reactive enough so that it can substitute Cl atoms. So CH3 minus would come, attack, remove Cl minus and one methyl gets attached. Then you get, the first step is you get CH3 COCl. One Cl gets replaced by one CH3 group. It is still reactive enough. So you get another CH3 substituting this and you get this. Same reagent. I mean, this is just the intermediate step. I'm just putting this in brackets. So just add zinc, add COCl2 phosgene, and you find you directly get acetone. This is a slightly different off-track reaction, but what is the importance of zinc? See, had I used Grignard reagents, then the problem would have been that it won't stop at acetone. Grignard would further attack, give you a third attack, one more methyl will add, and you would get tertiary butyl alcohol. In case you're using dimethyl zinc, which is less reactive, it stops at ketone and it does not give you any further addition, and acetone becomes the major product. This is a second, a little difficult, but maybe not difficult, but you might not be familiar with this concept of dimethyl zinc. In case you use that, this is also a very good conversion, very efficient, very nice. But 1E into but 2E. Now this is most interesting. I have but 1E. What do? Well, add HBr. HCl is cheaper, add HCl. what do you get? You get H and Cl, this as the major product, Markovnikov oxidation. And now use alcoholic KVH and heat. You would have elimination reactions, and this is beta 1 and this is beta 2. This is the major product you obtain. Is it fine? Yes, it is. T. 1-chlorobutane to N-octane. Just imagine butane to octane. From 4 to 8, you are doubling it, that means you are coupling it. You have Cl and I hope you can imagine what is exactly happening. What? You're making a bond, you're forging this new bond, you're removing Cl and making a carbon-carbon bond. This is classic Woods reaction. You add sodium in dry ether. One step clean and you get an octane from 1-chlorobutane. As simple as that. Benzene to biphenyl, very similar. You have benzene, yes. And if you want biphenyl, what is biphenyl? This is biphenyl. How can I get biphenyl? I use Word's fatigue reaction. If I have chlorobenzene and if I use sodium in dry ether, NaCl would be removed and this gets coupled. So all I need to do is to convert benzene to chlorobenzene. And how would I do that? That's again simple. Chlorine AlCl3. Electrophilic aromatic substitution on benzene will give you chlorobenzene, and from there you can get, by Watt's fatigue reaction, biphenyl. Simple. Explain why the dipole moment of chlorobenzene is lower than cyclohexyl chloride. Beautiful. Let us take a look at cyclohexyl chloride, this, and chlorobenzene. Now, first of all, please understand that chlorine is an electron withdrawing group. Yes, very much. It is an electron withdrawing group. So it withdraws electrons away from now this is sp3 hybrid carbon. Less electronegative, so chlorine can take away electrons more easily. It has some dipole moment, fine. When you look at benzene ring, there are two problems. Number one, carbon is sp2 hybridized. sp2 hybridized is more electronegative than sp3. Okay, so benzene ring will not allow the electrons to be taken away very easily by Cl atom. That is the first problem. So that reduces the dipole moment. Fine. Anything else? This itself would have been a sufficient reason, but there is a bigger problem awaiting us. What is that? It is the plus M effect of chlorine. This lone pair gets delocalized in the ring. Ting tang like this. So, although because of inductive effect, chlorine, because of higher electronegativity, it takes away electrons, yes. But because of resonance and delocalization, the lone pair tends to come back because of pi delocalization. So this coming back of lone pair on Cl atoms into the benzene ring, Cl is trying to take away electrons and pi electron cloud is trying to again come back in the ring system. So this opposite direction flow of electrons, pi electron cloud, again reduces the dipole moment of chlorobenzene as compared to cyclohexane. As simple as this. Explain why alkyl halides, though polar, are immiscible with water. Which substances actually are miscible with water? Well, the ones which can undergo hydrogen bonding with water, right? Alkyl halides in general, Rx. Please understand, R group is hydrophobic. Yes. So that itself creates a problem. And if you look at halogen, whether it is Cl or Br or I, it is not strong enough to undergo any kind of hydrogen bonding with water. So yes, they are polar indeed, but again, since none of them undergoes any significant hydrogen bonding with water, you normally find that water doesn't like them much, and hence they are immiscible with water. Grignard reagents should be prepared under anhydrous conditions. Very much. Why? Because Grignard reagent RMgX is a very powerful base. It is very reactive. It reacts completely with water. The moment it senses water, it takes away H plus from water. And you find this R takes away H, becomes RH. And all you are left with is MgOHX. So since Grignard reagents completely and instantaneously react with water, they must be prepared under anhydrous condition, even if there is a trace of water vapor, of water, any tiny bit of water also, it would completely and irreversibly react with Grignard and destroy Grignard. That's why Grignard can be only prepared under anhydrous conditions. Well, give the uses of Freon 12, DDT and CCl4 in iodoform. Let's take one by one. Freon 12 is very interesting. When it was discovered around 100 years back, scientists were all swooning over it and gaga about it. But then there are problems associated with it. But before that, see, CF2Cl2, dichloro-difluoromethane. It is sold by a commercial name called Freon 12, right? Right. And Freon 12 is a very popular refrigerant. It is used in the cooling system of all air conditioners and refrigerators. That is a very major use. Anything else? Later on, because it was cheap and inert and it was considered quite safe. It was also used in deodorant sprays. You know, you have those people spraying deo all over them like stupid people. So, Freon 12 was used because it doesn't have smell. If you're using fragrances are costly. And you don't want to really fill the entire spray bottle with fragrances. So most of it is Freon 12, which is used to create pressure. And with pressure, some fragrance comes out, or a tiny bit of it. So they're used in body sprays, hair sprays, etc. Yes, but there's a problem. What? This is an ozone killer. If you're using too much of Freon, as it gets released in atmosphere, it travels to the upper atmosphere, stratosphere, and it begins to decompose ozone there. And this ozone layer prevents sun rays, the ultraviolet sun rays, from reaching Earth properly. Now, the moment you remove this ozone layer, more UV rays start reaching the Earth, and if they start hitting the Earth, that means, again, life would be destroyed. So, each time you're using that fancy body spray, you're destroying Earth. Remember that, and that is why people have now started using, they have now started discouraging the use of Freon 12. DDT, dichloro-diphenyl trichloroethane. DDT was, every government's favorite compound, insect killer, mosquito killer, anti-malarial, anti-dengue drives. People used to spray DDT everywhere, etc., etc. Very popular insecticide. That was the only use. Unfortunately, DDT is now a very well-known carcinogen. It causes cancer. So, there are people who are avoiding it now. And then there are people who say that rather than dying from mosquito bite and dengue, I would rather take cancer, because cancer is not guaranteed, but dengue is guaranteed. So there are people still using it, but again, it's not safe. What about CCl4? CCl4 is much more popular. It was used, sometime back in dry cleaning. Means you take CCl4, you wash clothes with it, all the dirt and oils and greases, they dissolve in CCl4, and you get a clean cloth. So it was a very popular degreasing agent. You want to remove grease, grime, oil-based things, you wash it with CCl4. Yes. CCl4 is very inert. It is one of those organicish compounds which does not catch fire. Okay. So it was used in fire extinguishers. Well, that's the second use. Then, thirdly, it was also used as a starting material for manufacturing many chlorofluorocarbons. Like, you want CF2Cl2, you just start with CCl4 and you replace 2Cl by 2Fs and you get CF2Cl2. In that sense also it was very easy and a very good thing to use or start with. In general, CCl4 is a very popular inert solvent. It doesn't react much, it's heavy, it dissolves many organic compounds very easily, and these have been 3-4 very major uses of CCl4. What about iodoform? Antiseptic. It's slightly sharp smelling, not very pleasant, but iodoform when applied on skin used to release I2, iodine, very easily, which was very popular antiseptic, and that is why it was used. Nowadays people don't care for it much simply because of unpleasant smell. I'm just removing myself so that you can take a screenshot and use it if you wish. Well, write the structures of the major organic product in each of the following reactions. Wow, let's take a look. You have CH3, CH2, CH2Cl, NaI in acetone, Finkelstein's reaction. Halide exchange reaction, you get CH3, CH2, CH2I, and NaCl precipitates out. Finkelstein's reaction, classic SN2 reaction. We have tertiary butyl bromide with KOH, ethanol and heat. Wow. Now, alcoholic KOH, popular elimination stuff, and tertiary butyl bromide is a classic recipe for elimination. What happens is this. Just watch. If you have OH minus attacking, it goes off, and yes, it can always push away Br, and what you get is CH2, a very classic dehydrohalogenation reaction. This is what is called as E2 elimination mechanism. Halogen and hydrogen. This is, as you can see, alpha carbon, beta carbon. All these three are beta, they are same, identical. You remove H plus from anywhere, you get alkene like this. So isobutylene is the major product in this case, and although it has not been asked, but the mechanism would be E2 in case you find it relevant. Well, we have CH3, CH, CH2, CH3. We have 2-bromobutane. And you have aqueous NaOH. Now, aqueous OH minus, this is, that mostly promotes SN2 substitution, and at least with secondary alkyl halides. So, if you use OH minus, you have predominant SN2 attack, and Br gets substituted by OH. As simple as that. CH3, CH2Br with aqueous ethanol and potassium cyanide. Cyanide is a classic nucleophile. Attack. Beautiful and fast and quick and rapid SN2 reaction. And you get CH3, CH2, Cn. This is the reaction which is going to happen easily, happily, and quickly. C6H5ONA plus ethyl chloride. Now, if you just see, in this case, you have a strange nucleophile, the huge and bulky phenoxide ion, and you have CH3, CH2, Cl. How do they react? Can you draw the arrows and show me the reaction? That's not difficult. Attack, crack. Whichever carbon to which halogen has been attached is the alpha carbon, and that is the site of reaction. What happens? What do I get? It seems I am in for an ether. Yes. I get ETOPH plus, of course, Cl minus goes away. You have NaCl. You can use it for cooking food, making whatever. Yeah, there we are. You have propanol and SOCl to the very famous thionyl chloride. This is Darson's reaction. What do I get? SOCl2 replaces OH by Cl. It is a halogenation reaction, I get CH3, CH2, CH2, and the change happens here. I get Cl and SO2 and HCl. The most beautiful part of this conversion is that all the other products are gaseous. SOCl2 is a gas, SO2 and HCl are gas. If you use excess of SOCl2, all the alcohol reacts away, so it is the limiting reagent, it gets exhausted. So the product can be pure propyl chloride, and this purity of product is so valuable that it makes Darzin's reaction a very favorite reaction. We have 1-butene with HBr in presence of peroxide. And this is crash effect or anti-Markovnikov addition. What do I get? I get H and Br added like this, anti-Markovnikov, 1-bromobutane. That is the answer, and the mechanism goes by radical mechanism. Well, let's take a look. CH3, CH, double bond C, CH3, CH3, like this. This is what I have, and I am trying to add HBr. First of all, if you add H+, what happens in electrophilic addition? Well, you find the more stable carbocation is formed. If H gets added here, I get a tertiary cation which is more stable indeed, and this is very much in accordance with Markovnikov's rule also. Hydrogen will go to that carbon which has more hydrogens. This already has one hydrogen, this has no hydrogen. And then Br minus gets added. So I get ting, tang, ting. This is the major product. Yes, that is the answer. Now it says, write the mechanism of the following reaction. You have N-butyl bromide with potassium cyanide. Ethanol water mixture is actually the solvent, and I get cyanobutane as the product. How do we do that? Well, this is N-butyl bromide indeed, and if we are using cyanide, what happens is a backside SN2 attack. Wow. If you just look at it, if you want me to elucidate it more, see, look at this carbon. This carbon is attached to a Br atom. Yes, it has H, it has H, and it has 1, 2, 3. That means it has a propyl group also, like this. Fine. Now, exactly from the opposite side, I'm explaining even with confirmations, everything. Br, please remember, is leaving group. Lg. Lg, Lieutenant General, no, it is leaving group. And exactly from the side opposite to that of leaving group, there is attack. Oh my God. Cyanide attacks. And as it attacks, what happens is, let me show you the intermediate stage. First of all, this is tetrahedral geometry. You have Br here, and you have, like in this fashion, H, alkyl group like this. When temporarily cyanide attaches itself, you have Cn and you have Br. Cn is coming out, Br is being pushed out. I have trigonal bipyramidal geometry. You would see H, and propyl group like this. And once Br is pushed out, this is transition state of course. And once bromide is pushed out, cyanide settles nicely. You have Cn like this. There is inversion of configuration. This H goes on this side. All this, whichever is on this side, goes to that side. So I have H, and I would have propyl group like this. This is it. Honestly, this is not chiral, so inversion of configuration has no significant meaning here. But nonetheless, with all the details, this is the mechanism of the reaction. Arrange the compounds in each set in order of reactivity towards SN2 displacement. Now, I have 1-bromo 2-methyl butane. No, sorry. This is 2-bromo 2-methyl butane. Fine. Now, this is tertiary, and tertiary is very ugly when it comes to SN2 reactions. Then I have one bromopentane, which is primary, which is very beautiful. And then I have two bromopentane, which is secondary, not so beautiful, but at least better than tertiary. So, which is the highest? Highest is this. This is more than secondary, and secondary is more than tertiary. So, I'll just rewrite this tertiary here. That way. This is the correct order? Yes, this is the correct order. What is the reason? The reason is steric hindrance. From primary to secondary to tertiary, backside attack becomes more and more difficult because of crowding of alkyl groups, and that is why the rate of SN2 reaction decreases. Arrange the compounds again. SN2 displacement. Well, what do we have? We have 1 bromo 3 methyl butane. Let us have butane. 1 is bromo. 1, 2, 3 is methyl. Fine. And then I have 2 bromo. 2 methyl butane. Very ugly. Why? This is tertiary and this is primary. Primary is way faster as compared to tertiary. And then what do I have? I have butane, I have 2 bromo and 3 methyl. Fine, this is secondary. You know very well, from primary to secondary to tertiary, as the crowding increases, the rate of reaction decreases. I'll just rewrite this. The order is, well, this is the rate of increasing order. Just this is a part of rough. I have rewritten this, don't worry. This is the correct order. Why? Reason is same. From primary to secondary to tertiary. If you look at this alpha carbon, as it becomes more and more crowded, backside attack becomes sterically hindered, difficult, and rate of SN2 decreases. Simple reason. Third one, I have bromobutane. Lovely. I have 1 bromo, 2,2-dimethyl propane. 2,2-dimethyl, this is horrible, neopentyl bromide. And then I have 1 bromo, 2-methyl butane. Okay. I have butane, 1 bromo, and 2 methyl. Okay. And then I have 1 bromo and 1, 2, 3 methyl. Okay. So just imagine as if this methyl group is traveling on, you can imagine this very well, that's not difficult. This methyl group is here, it is pushed to the further place, and the same methyl group, now this is 1, 2, 1, 2, 3. This is 1, 2, 3. 1, 2, 3, 4. Like this. And it just vanishes. Now, I hope you can see that this is primary, this is primary, this is primary, and this is also primary. All of them are primary, yes. But if all of them are primary, then what is it that you consider? Look at the neighbor. If you're going to a place where neighborhood is very dirty, difficult to enter, you can't really enter that space, right? You know? So, just see here. In this case, this is very free and fair. 2, 3, it's not crowded. The moment you see there's a branching at 3, it is far away. It's not that bad. But still, if there's no branching at all, it is free. So, this one will have a slightly better rate as compared to this one. As this branching gets near, it gets worse. And if there are 2 branches on the adjacent atom, it is very, very poor. Yes. Is this the order? This is the order, and steric crowding is again the reason for this. Out of benzyl chloride and, well, I have, this is pH CH2Cl, and I have pH CHCl, pH again, which is more easily hydrolyzed by aqueous cleavage. What happens with aqueous cleavage? If you just take a look, what happens is, this can dissociate as pH CH2+. You have a benzyl cation. And what happens is that this benzyl cation has a positive charge which is stabilized by plus M effect from benzene ring. Oh wow. So this positive charge can roam around. It is highly stabilized. Beautiful. So very easily if you can create benzyl cation, fast is the reaction. Yes. So does benzyl chloride undergo easy hydrolysis or reaction with KOH? Indeed it does. But if you look at double benzylic cation, something like this, what happens is you get pH, CH, pH like this. What does that mean? It means that if I have not one but two benzene rings, do you see that extent of delocalization is much more? Why? Not just one, but two benzene rings are donating electrons like this from here, or they could donate from here also, like this and this and this. Not all everything simultaneously, either from here or from here. Overall, it's huge delocalization. Two is obviously better than one. This is more stable carbocation. More quickly formed, which implies faster reaction. Right? So out of these two, the second one is more easily hydrolyzed by aqueous KOH. And what is the answer? What is the product? Product is Cl gets replaced by OH. So in this case, you get C6H5 CH2 CH2OH, and this gives you pH, CH, pH, OH like this. And this is faster, much faster. Para-dichlorobenzene has higher melting point than ortho or meta. Discuss. See, para-dichlorobenzene is very symmetric. It can be neatly stacked one over the other, nicely in crystal structures. In crystal structures, because of symmetry, it can form very good fitting. On the other hand, if you have ortho or para, their fitting in crystals is not as beautiful or as comfortable. Because of that, see, better the packing in crystal structure, higher is the melting point, and hence para would have higher melting point as compared to ortho or meta. How the following conversions can be carried out? Now, this is a long question with 20 subparts. Very interesting and very informative and very, very knowledge enhancing. So pay attention and focus. Propene, you wish to convert to propane 1-all. If you just take care and look, what all do you have? Propene, fine. And the moment you want to convert this to propane 1-all, means you want to add H and OH. Hydration of alkene means addition of HOH or water. And this, my dears, is anti-Markovnikov addition. Anti-Markovnikov addition. What is the method for anti-Markovnikov hydration of alcohols? Hydroboration, oxidation. First, you add diborane B2H6 NTHF solvent, and then you add H2O2 with OH minus. The moment you do this, you have HOH added in anti-Markovnikov fashion without any absolute rearrangement. This is the solution. Ethanol to but1-ine. This is a repeated question. We have converted ethanol to but1-ine as the very first part of the previous question 10.10. The 10th question first part is exactly the same. So since it is repeated question, there is no need for answering that. It's a good question, but we have already answered that. Look at the beauty of NCERT. They have repeated questions. And then we have 1 bromopropane to 2 bromopropane. Very interesting again. 1 bromopropane changes to 2 bromopropane. How do we do this? We could actually do this in 2 steps. If you have propene by any chance, and if you add HBr by Markovnikov rule, you will surely have 2-bromopropane. And how do I get alkene? Well, you take alcoholic KOH and you heat it. You get alkene. So 1-bromopropane, heat with alcoholic KOH, you get propene, add HBr. As per Markovnikov's rule, you get 2-bromopropane. This is the method. Toluene to benzyl alcohol is again a repeated question. But, well, let's see how do we do this. There are many methods. Heating with freshly precipitated manganese dioxide can do this in 1 step, yes. But a more classical method as per NCERT would be, you take chlorine and HNO. You get CH2Cl and simply add aqueous KOH. You get benzyl alcohol. This is one method. Or, let me change color to denote the difference. You could use NBS, N-bromosuccinimide, and very selectively you get benzyl bromide, and same aqueous KOH would give you again benzyl alcohol, whichever way you want. I've told you 3 ways, and there are still more, but enough, right? 5th, benzene to 4-bromo-nitrobenzene. Now you have nitro and you have bromo both. How do we do it? Please note, nitro is meta-directing group. If I add nitro before, then I would have to add meta to it. Bromo, Br group is ortho-para-directing. This is good. So I use bromine with AlBr3 and I get bromobenzene. Very good. Benzene is a big group. It is ortho-para-directing, and because of its bulk, ortho is not good, so it is typically para-directing. So what do? Then I carry out nitration. I get para, yes. This is major product. I will also get some ortho product also. I'm not saying I won't get. This is minor. Fractional distillation. Fractional distillation will easily separate them, and you have this product, and this is what you wanted, and this is what you get. Important part is, please do not carry out nitration first, because nitration is a major deactivator, and also it is meta-directing group in case you have NO2 before, so you would get meta-bromo, not para-bromo in that case. Got it? Right. 6th question, you have benzyl alcohol. And you wish to convert this to 2-phenyl ethanoic acid. Very interesting. This OH, you wish that it changes to COOH. How do we get that? That means you are planning to add 1 carbon atom. See, it is not just important to get the answer, it is important to get the idea. How do you get that? Now, a very good idea of adding carbon atom with COOH group is add a cyanide group. Just imagine, if I have CH2CN, right? And if I boil this with H plus H2O, cyanide is always hydrolyzed to COOH. Yes. Will I get this? Yes. What happens to nitrogen? Nitrogen forms NH4 plus and you can separate it. It is separated automatically. If I get the cyano derivative, it will give me my product. Now OH, instead of changing it to COOH, now my job is limited to changing OH to CN. Now OH is not a group which is very easily removed, But I could actually change this to chloride by simple PCl3. Wow, yes. I have this, and chloride has to be changed to cyanide, my dear. Come on. Let's not be ashamed. Simply add potassium cyanide. SN2 attack, classic substitution, very easy and very beautiful. I would get, it's a strong nucleophile, potassium cyanide, chloride changes to cyanide. 3 steps. Add PCl3, potassium cyanide, followed by acid and boiling, and you get your desired product. This is the method. Ethanol to propane nitrile. Ethanol. This is 1, 2, 3. Propane nitrile. Well, what has happened? This OH has changed to cyanide, CN. Remove OH, add CN. Now you know this, come on. We have just done that. Add PCl3. You get, instead of OH, you get Cl. Yes. And Cl, add potassium or sodium cyanide. Classic SN2 attack. You get this plus KCl. Simple, beautiful 2 steps. And you have this, right? The next one, aniline to chlorobenzene. Now NH2 group you have intentions to remove, and you want to change it to Cl. How do we do that? 2 steps. Once again, first is diazotization, NaNO2, I'm sorry. This is NaNO2 dilute HCl. The moment you have NaNO2 or sodium nitrite, what happens? You get HNO2. HNO2 reacts with NH2 group, primary amines, and it forms a very classic compound, benzene disonium chloride, BDC. Benzene disonium chloride. And now it appears that your assignment is to change this BDC to chlorobenzene. Do you remember any reaction? Yes, Sandmeyer's reaction, indeed. How do you do this? Cuprous chloride. Sorry. Add KCl with CuCl. And you find chloride. It's a radical mechanism reaction. You get chlorobenzene. Nitrogen, of course, gets liberated. And, you get chlorobenzene. In short, Sandmeyer's reaction. Yes, indeed. 9th, 2-chlorobutane to 3,4 dimethylhexane. Now this is 2-chlorobutane. It has 4 carbons. 3,4 dimethylhexane. 1, 2, 3. And now we have 4, 5, 6. 4, 5, 6. Yes. And if you notice carefully, we have 1, 2, 3, 4 dimethylhexane. If you just care to see, yes. Can you see the same thing which I am seeing? We don't know, sir, what you're seeing. Well, let me show you this. If you just care to notice, well, this is your reactant, yeah. And what about the product? And this looks like the product. I just write it twice, the same molecule. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'm just motivating you to imagine. How's it? Yeah. You place 2 molecules and you just couple them, you just add them. How can you do that? Well, Wood's reaction. So all I need to do is just add sodium in dry ether. That's it. I have shown you the trick here. The way in which it gets joined. Just simply two molecules combined. This is the new bond which is formed. This is the new bond which is formed. They just add Wood's reaction and you get this. That's it. 10th, you have propene, 2-methyl 1-propene, fine. 2 propane, 2-chloro 2-methyl propane. That doesn't sound very difficult. What they're doing essentially is they're adding HCl. What do? You just add HCl. It's Markovnikov's addition, nothing else. You add HCl, you get this. Simple. Most branched, hydrogen atom gets attached preferably to the carbon which already has more number of hydrogens. This has 2, this has 0. H goes here, Cl goes here. It is simple Markovnikov's addition. That's all. Add HCl. Ethyl chloride to propanoic acid. We just did something very similar. From 2 carbons, you are going to 3 carbons. That means you have to add 1 carbon and it has to be COOH group. Imagine you have cyanide here. When you imagine COOH, imagine cyanide. That's a trick. And if you just add acid, you add water, you boil. You get carboxylic acid. Fine. How do I get cyanide here? Come on. Add sodium or potassium cyanide. That's it. You could use ether solvent, which is fine. Other solvents are also okay, but simple 2 steps. You add carbon using cyanide, then hydrolyze. That's it. Simple enough. 12th, but1ene to N-butyl 1, 2, 3, 4 iodide. N-butyl iodide. How do we do this? Well, as you note, this seems to be anti-Markovnikov addition. And we know very well that anti-Markovnikov addition cannot be done by HI or HCl. It is done only by HBr. So, what do? We add HBr in presence of peroxide. Radical mechanism, I get H, I get Br. But I don't need Br, I need I. Okay, take it easy. Finkelstein's reaction. Add Ki in acetone. SN2 attack. I minus moves in, KBr gets precipitated out. From acetone, I get these 2 steps. First is peroxide effect, HBr addition, anti-Markovnikov, followed by Finkelstein's reaction. You have 2-chloropropane and you want propane 1-ol. Now this is interesting. How do you do that? Not difficult again. How do you do this? Get propene. How? Alcoholic KOH, heat. Propene to propane 1-ol, anti-Markovnikov addition of water. Hydroboration, oxidation, we started with that, right? So you add B2H6 in THF or any dry ether, and then you add H2O2 with basic medium. You get anti-Markovnikov addition of HOH, and beautifully you get this. Simple, direct 2 steps. Good enough. Isopropyl alcohol to iodoform. Oh my God. How do you do this? Well, for iodoform test, you need methyl ketone. So what do? We oxidize this to acetone. How? Just use K2Cr2O7 or K2CrO4, any oxidizing agent. You oxidize isopropyl alcohol to acetone, and then iodine, base, heat. Heat it with iodine and a little base. You get iodoform very beautifully along with CH3COO minus, which we throw away. We get as much iodoform as we wish. That's how. Chlorobenzene. Wine, fine. And we are changing this to para-nitrophenol. OH and NO2. Fanciful. How do we do this? We can carry out nitration, yes. How? On which grounds? Where? If you have, there are two ways to do this. Let me tell you both the ways, then I'll ask you a good question also. Method 1. We use what is called as Dow's process. We have chlorobenzene. By Dow's process, we use NaOH, 350 degrees Celsius, high pressure, and we get phenoxide ion like this, which is okay. Now you just cool it down, add acid, you get phenol. And this you can use for nitration. Conc HNO3, Conc H2SO4. OH group is ortho-para-directing, so I get OH NO2. Of course, I also get one more OH NO2. This is steam volatile, I can remove this, this remains, so I get this. They can be removed by distillation. This is one method. Is it good? You have to tell me this. Is it good or bad? But then I'll tell you this is method 1. And what is method 2? Let's take a look. Chlorobenzene, right? Now we have nitro and phenol. Let us first try for the nitro business. Yeah. Let's do nitration first. Conc HNO3, Conc H2SO4. I would get ClNO2 and I will also get ClNO2. Which we separate by distillation. Now this Cl and NO2 is there. Because of this NO2, Cl gets activated for nucleophilic aromatic substitution and I heat it with Conc NaOH. Not to 350 degrees Celsius, just concentrated NaOH. If I heat, I get a substitution. Beautiful, like this. This is the way we do it. And that's it. Maximum, at the end you acidify just to make sure that H plus is here. So, 2 steps. First this and second this. Now, this is method 2. I also told you a method 1 in which we first did attached OH group and next we did nitration. Which is the better method? First or second? Second is the better. Why? Please remember, once you have made phenol, in method 1 we made phenol and then we carried out nitration, and during nitration most of the phenol gets destroyed because it is highly reactive. So it is more useful to first nitrate it and then convert it. Yield will be better. Second is a superior method as compared to the first one. 2 bromopropane to 1 bromopropane. Come on, this is very simple. And the way it goes is, you have 2 bromopropane and you want to convert this to 1 bromopropane. This does not require a genius. Just think about this. Come on. The simplicity is just add alcoholic KOH. So many things have similar step like this. And then carry out bromination. HBr in presence of peroxide. This looks like a repeated question nonetheless. And you get anti-Markovnikov addition and you get H and Br added like this. Radical mechanism of addition. This is how you get it. Chloroethane to butane. Life just could not get simpler. How? You get this red bond. Wurtz reaction once again. Sodium and dry ether. 2 carbons going to 4 carbons. 1 step straight, flat, no greatness involved. Benzene to biphenyl is again a repetition. Old questions have been shamelessly repeated in NCERT, which is a hallmark of NCERT. How do we do this? Well, AlCl3 and chlorine. You get chlorobenzene and then you use Wood's Fittig reaction. How? Sodium and dry ether. Mechanism is radical mechanism and you get biphenyl like this, straightforward. All this was a part of question number 10.10. Same parts have been repeated with utter shamelessness here. Tertiary butyl bromide to isobutyl bromide. This is tertiary butyl bromide. And if we wish to convert this to isobutyl bromide, this means that Br should come here. Okay. How? The drama is very similar. First, alcoholic KOH, heat. You get isobutylene. And then, come on, tell me this. Add HBr, anti-Markovnikov addition, in presence of any peroxide like benzoyl peroxide. This is HBr addition like this, and you get isobutyl bromide. Last and the least in this section, aniline you wish to begin with, and phenyl isocyanide would be this. Carbamine test, how do you wish to do this? Add chloroform, add KOH and heat. This is all you need to do to get isocyanide like this. That's all. Question number 20, which says treatment of alkyl chlorides with aqueous KOH leads to formation of alcohols. RX, aqueous KOH gives ROH. Okay. But in presence of alcoholic KOH, alkenes are the major products. Explain. See, this is a substitution reaction, classically, typically SN1 or SN2. And this is elimination E1 or E2. So the question is, by changing the solvent from aqueous to alcoholic, why is it that the substitution reaction actually changes to elimination reaction? Although NCERT has oversimplified this, it's a very unfortunate misconception. Let me first tell you a disclaimer. I'll explain what they want to say, etc. But this is true only for secondary alkyl halides. Properly and honestly, it is not true for primary or tertiary. It is true only for secondary. NCERT has been happy enough to generalize it to everything, and it has become a very, very popular misconception now. So I'm not going to just analyze that. I'll just say, why does this difference in solvent change the mechanism? Let me talk about that. You first need to understand the basic behavior of solvents. In aqueous solution, KOH is totally dissociated, nearly totally. That means it is present as K plus and OH minus ions. Not just that, this OH minus ion is heavily solvated. What is the meaning of solvation? It is surrounded by water molecules. Okay. So if OH minus is surrounded by water molecules because of very strong hydrogen bonds, great. Understand that this is a more polar medium. As a solvent, water is more polar. You have OH minus ions, and these OH minus ions can serve two purposes. Number one, they can act as a base, yes, and number two, they can also act as a nucleophile. Indeed. Now, just shift over to another solvent, alcoholic KOH. In alcoholic KOH, you have EtOH plus OH minus, and they form EtO minus with H2O. So actually, in alcoholic KOH, you also have alkoxide ions. Alkoxide ions are bigger and huger, right? So EtO minus is bulkier than HO minus. Obviously, ethyl group is much huge as compared to hydrogen atom. If it is bulkier, this means EtO minus is a poorer nucleophile. If it is giving SN2 attack, it is going to face more resistance because it is huge, it can't enter. OH minus is smaller, it can quickly and easily enter. So ETOH minus is a poorer nucleophile than OH minus. Okay. If it is a poorer nucleophile, but both of them are good bases, across the internet I have found a statement, ETO minus is a much stronger base than OH minus. That's not correct. Their basic strengths are roughly same. Had ETO minus been a stronger, much stronger base than OH minus, then a weaker base OH minus could not have made a stronger base ETO minus. It is true that ETO minus is slightly stronger. Yes, not much. But roughly they have similar basic strength. But the correct reason is, sorry, that ETO minus is a much weaker nucleophile because of huge bulk. Therefore, substitution reactions with ETO minus is not encouraged, is not favored. OH minus is a strong base, yes. Is it also a strong nucleophile? Very much indeed. And please note, again, there are rumors like OH minus because of hydration or solvation becomes weak base. That is stupid. If it becomes a weak base, it also would become a weak nucleophile also. This is not correct. The correct reason is bulk. This is bulky. Attaching is difficult. Substitution is difficult for ETO minus. On the other hand, when you're talking about elimination reaction, elimination involves just taking away one H plus and running away. ETO minus is good at that. ETO minus is going to approach, steal one hydrogen atom and run away from outside. It doesn't have to go very close. It doesn't have to get attached to the molecule. So, substitution with ETO minus is not favored. Therefore, elimination happens. And we get alkene OH minus. It's a good base, yes. It's a good nucleophile also, yes. So can it not give elimination? It can. But at the same time, it also tends to favor substitution simply because of its thin and slender size. It can very well go within the molecule, attack very easily and get itself attached. So it gives you a very good dose of substitution reactions as well. Primary alkyl halide C4H9Br. Please note it is primary. A. Reacted with alcoholic KVH to give a compound B. Now C4H9Br, A, which is primary. It says it reacts with alcoholic KVH to give a compound B. When B is reacted with HBr, it gives C, which is an isomer of A. Well, C, they are telling me, is an isomer of A. Fascinating. When A is reacted with sodium metal, it gives a compound D. Now I have to give a Wood's reaction, it gives D. And D is C8H18. C8H18, which is different from the compound when N-butyl bromide is reacted with sodium. So this is not equal to. Now if I react N-butyl bromide with sodium, see, this is butyl. N-butyl bromide would mean that I have Br and Br here. And if I make it undergo reaction with sodium, it means that these bromines would be removed. And what I would get? I would get N-octane. So this C8H18 is not equal to N-octane. This they have very clearly mentioned. Fine. Give the structural formula of A and write the equations for all the reactions. We have been given major hints, so let's try. The very first hint is this is primary. Now if I have a butyl bromide how many butyl groups do I get? Well, there is an N-butyl group, 1, 2, 3, 4. Then there is an isobutyl group. Then there is a secondary butyl group. And then there is a tertiary butyl group. So I could have had these 4 options, but I am being told that this is primary. If this is primary, it means that, well, I don't have tertiary or secondary as offers. This is not the case. If this is ruled out, I'm just left with 1 and 2. But I am told at the end, please don't match it. This is not the case. If this is not the case, well, then it's seemingly I'm left with only one option, and this is isobutyl bromide. So most probably A is isobutyl bromide. Now let me try. If I do use alcoholic KVH, B would be isobutylene. With HBr, I would obtain tertiary butyl bromide. And if I react this tertiary butyl bromide with sodium, I would get something like this. This is what they are saying. This is what I'm expected to get, which is not same as N-octane. Well, it sounds okay. Could there be any other offer? Well, let me explore this also. Had I had this second primary, 1, 1, 2, 3, 4, had this been N-butyl bromide, with alcoholic KVH, I would have obtained this. With HBr, I would have obtained this. And with sodium, I would have obtained, well, something like the 1, 2, 3, 4, 5, 6. Yeah. This would have been the answer. So these both seem to be having a kind of favor with us. Primary alkyl halide, this. Is this primary? Yes. Is this primary? Yes. It is reacted with alcoholic KVH, it reacts. I'm trying out 2 options. To give a compound B, I get compounds B's. B is reacted with HBr, well, I give Markov-Dikov addition. To give C, which is isomer of A. Is C an isomer of A? Yeah, it is isomeric, fine. What else? When A is reacted with sodium metal, it gives compound D. A with metal gives D, yes. Which is different from an octane. We very well agree it is anyway different from an octane, big deal. That last step is pretty useless. This was anyway not being formed. So, what are the offers? Well, structural formula of A, 1 and 2. As per NCERT, both of them are seemingly the answers. Is there a superior and an inferior answer? Yes. This is a superior answer, and this is, I'm not saying wrong, but an inferior answer. Why? Because Wood's reaction is never good for tertiary cases. Wood's tertiary alkyl halides give less efficient Wood's reaction as compared to primary or secondary. So this seems to be a much more, a much better candidate for option D as compared to that one. But that is not impossible, let me tell you. So this question actually has 2 answers, not 1. This being a more significant answer, and this also being a probable but not that beautiful answer. That. What happens when N-butyl chloride is treated with alcoholic KOH? 1, 2, 3, 4. N-butyl chloride. I'm sorry, this is chloride. Yes. If you treat this with alcoholic KOH, what you're expected as per NCERT is an elimination reaction. You read the word alcoholic and give you elimination. This is the superstition, and this is what NCERT desires you to believe. I'll not contradict them, although this is with tabs, but this is what you're expected to learn. Bromobenzene is treated with magnesium in presence of dry ether. This is bromobenzene. It takes a lot of time, but slowly it would take maybe an hour or 2 but you will get a Grignard reagent. Wow, an aryl Grignard reagent? Yes, you would get an aryl Grignard reagent. Chlorobenzene is subjected to hydrolysis. No, actually nothing happens. Hydrolysis means reaction with water. If you just add water, there is no reaction at all. Chlorobenzene fails to undergo any hydrolysis. Ethyl chloride is treated with aqueous KOH. Ethyl chloride, if you add aqueous KOH, it's a classic one-step SN2 reaction and you get ethyl alcohol. Wow. Methyl bromide is treated with sodium in presence of dry ether. This is classic Woods reaction. You get CH3CH3, ethane. A coupling reaction, very famous Woods reaction. And methyl chloride is treated with potassium cyanide. Well, poisonous though it may sound, it's a classic case of, well, SN2 attack. You get CH3, CN. We get methyl cyanide, ethane nitrile. This is what you get. That's the reaction. So dears, this was NCERT, Haloalkanes and Haloarenes. Complete solutions with explanations. And the target is not only the gaps of theory should be filled, we should revise all possible theory and to discuss the answers. I hope you find them useful. We'll meet again for a different chapter.